Hi everyone, in this lesson we'll look at how to factor special products part 2. So first we're going to look at how to expand a plus b squared. So remember that when we expand a plus b squared, this actually means a plus b times a plus b. When we expand this, it's going to expand to a squared plus 2ab plus b squared. So that gives us one identity. When we expand a plus b squared, we're going to get a squared plus 2ab plus b squared. And if you're not sure how I got that, just FOIL this and combine some like terms and you should get this trinomial. Likewise, when we expand a minus b squared, again we should get two terms. A mistake that a lot of students make, or we should get three terms rather. A mistake that a lot of students make is that when they expand this, they only get two terms. They think that they just square a and square b, which is not the case. We're actually multiplying a minus b times a minus b. And again, when we expand that, we get a squared minus 2ab plus b squared. So in this case, the middle terms are, or when you have a minus b squared, the middle term is going to be opposite in sign. So this gives us another identity, and of course, if you're really fast, or if you're good at expanding this, you should be able to go from a minus b squared directly to a squared minus 2ab plus b squared once you get familiar with the identity. So we can exploit this pattern to factor perfect square trinomials. So if we have a trinomial that we can write in this form, a squared minus 2ab plus b squared, or a squared plus 2ab plus b squared, we can use the symmetric property of equality to go from an expanded form into a factored form. So let's go ahead and we'll look at a couple of examples. So in this first example, I have 4x squared plus 12x plus 9. And I can rewrite this as, well, the first thing to identify is that 4x squared and positive 9 are both perfect squares. Okay, so this doesn't necessarily mean right off the bat that it is a perfect square trinomial, but let's see if we can rewrite it in this form that we have above. So we can rewrite 4x squared as 2x squared. We can rewrite positive 9 as 3 squared. And we can rewrite the middle term as 2 times 2x. Let me give myself a little bit more space here. 2 times 2x times 3. So now I've got this in the form that I have a squared plus 2ab. So this factors to, this is a perfect square trinomial because the middle term, 12x, is twice the product of the square root of the first term times the square root of the last term. So this factors to 2x plus 3 squared. So a fast way to check this is just to take the square root of 4x squared, which is 2x, take the square root of 9, which is 3, and multiply it by 2. So multiply that by 2 and see if that matches the middle term. And if it does match the middle term, then it's a perfect square trinomial. And it can be written in the form of a plus b squared, provided that the sign on b is positive. If it were negative, this would have been 2x minus 3 squared. And again, another important thing to note is that when you're squaring binomials, if we go back up to our identities, both the first term and the last term are positive in both cases. So if this last term would have been negative, then this wouldn't have been a perfect square trinomial. And if this last term would have been negative, this wouldn't have been a perfect square trinomial either. So in our next example, we have 49x squared minus 126xy plus 81y squared. So again, if we tried to factor this just using guess and check or by using decomposition, it might be a little bit difficult because there's two prime factors of 49, and there's quite a few factors of 81. So using decomposition or using guess and check might lead to a lot of work. So the best thing to do here is to identify that 49x squared is a perfect square and 81y squared is a perfect square. So now we're just going to check to see that the middle term would give us a perfect square. So we'll take the square root of 49x squared, which is 7x, take the square root of 81y squared, which is 9y, and multiply that by 2 and see if that gives us the middle term in either positive or negative value. So 2 times 7, actually let's do this first. Let's multiply 7x times 9y, which is 63xy, times 2 is 126xy. So that matches the middle term, except for we have minus 2 times 7x times 9y. So we'll get minus 126xy. So this factors to 7x minus 9y squared. And I knew that this was going to be negative because the middle term is negative again. So in example 3, I have 3a squared minus 24a plus 48. Now, this is not a perfect square trinomial off the bat, but if you notice, if you look at all the coefficients in this trinomial, 3 is divisible by 3, negative 24 is divisible by 3, and 48 is divisible by 3. And I know that I might not remember that 48 is divisible by 3, but using the divisibility by 3 rules, if you add up the digits of 48, which are 4 and 8, so 4 plus 8 is 12. 12 is divisible by 3. That means that 48 is divisible by 3. So all that I did was I just added up the digits of 48, which is 12. And since 12 is a number that's divisible by 3, I know that 48 is divisible by 3. So that's a fast rule to decide whether something is divisible by 3 or not. So common factor 3 out, and we get 3 times a squared minus 12a plus 16. So now, a squared is a perfect square, 16 is a perfect square, and if we take the square root of the first term times the square root of the last term and double that, let's check to see if it gives us 12a. So the square root of a squared is just a. The square root of 16 is 4. Oh, whoops, sorry guys. Actually I made a mistake here. Negative 24a divided by 3 is 8a, not 12a. Sorry about that. So now, if we take the square root of a squared, which is a, and the square root of 16, which is 4, and we double that, that's equivalent to 8a, which matches our middle term. So this factors into 3 times a minus 4 squared, where this first term is just the square root of a squared. The last term is just the square root of 16, and I get the sign here by looking at the sign of the middle term. So in the last example, we have a factoring question where we're given 4 terms. Now remember that I said that if you have 4 terms and you're asked to factor, first try to implement a grouping strategy. And so what I could do is I could try to group together these first two terms and group together the last two terms, or group together these two terms and group together x squared and negative z squared. But the problem is that no matter how you change the order of addition and subtraction for this polynomial, you're not going to get terms that you can common factor. So you might notice something here, though, that x squared plus 2xy plus y squared is a perfect square trinomial. And z squared is a perfect square as well. So basically right here we've got a difference of two squares, because x squared plus 2xy plus y squared is a perfect square, and minus z squared is a perfect square as well, and we're subtracting minus z squared from this perfect square here. So let's go ahead and we'll factor x squared plus 2xy plus y squared. It factors to x plus y squared minus z squared. And now we have a difference of two perfect squares. So this factors to, if I were to make a substitution here, I could think about this as being, I don't know, like w squared minus z squared, which would factor to w, which is x plus y, plus z, times x plus y minus z. So I thought of, all that I did here was I just thought of x plus y as w. So we've got w plus z times w minus z, and I just factored this difference of squares into conjugates. So that's a nifty little trick for factoring when you have a difference of squares and a difference of between a trinomial that's a perfect square and another perfect square. So that concludes this lesson, and we'll see you in the next video.